there's a lot of information here, so way to show that. Anyways, Rebeca Corralejo Palacios, she's a doctorate student in Valladolid University, and she works in the biomedical engineering group of the University of Valladolid. The name of the paper, rather long, see if I can translate that correctly. Improving household accessibility, implementing a domotic application using BCI system, brain-computer interface, based on P300 potentials. And we are all looking forward to understanding what this is all about. So, Rebecca, thank you very much when you're ready. Well, as Stefan said, my name is Rebecca, and I work in the biomedical engineering group of the Valladolid University. This is an application that we're working on, and this should enable us to manage and control different electronic devices that we use in the household using a brain-computer interface system. This is the contents of my presentation. First, an introduction to BCI. The brain-computer interface system, what it does, it monitors brain activity and takes certain feature characteristics related to the feeling or the intention of a user, so that those characteristics can be translated into commands to control a device. A device could be anything from a computer to a wheelchair. Normally, the technique used to record brain activity is a brain scan, and it's non-invasive. But the aim of this is aimed at improving quality of life of people with severe disabilities, and it's been used to control domotics, such as the use of prosthesis, control of wheelchairs, even different tools to facilitate communication between people. As for brain-computer interface systems, I'm going to give you a brief classification. These can be distributed. We can have endogenous or exogenous systems. The endogenous BCI depends on the user's ability to control a certain characteristic of the brain activity. These systems include BCI systems using motor sensory systems, and the others are the low cortical potentials, the SCIPs. Now, one example is controlling a cursor in a dimension. For example, a typical example is a little point on the screen, and we have a bar on the other side. And to move that ball, what a person has to do is to imagine, not to do, but to imagine that you're moving your right hand or your left hand in such a way that based on which hand you're thinking of, the ball will move to one side or the other. So the endogenous systems, it is a user that mentally controls a characteristic of its brain, of the person's brain activity. In this case, what they manage is the amplitude of a brain wave between 12 to 13 hertz, and that varies depending on which hand we're thinking of when that's been recorded in the brain scan. On the brain cortex, which is the motor region of the brain related to movement, that is. And the drawback of the endogenous BCI systems is they need a training period. We need to conduct a number of sessions so that one can learn how to use these techniques and how to carry out these mental movements. The other BCI systems are the exogenous ones. And this will basically create this is the case, for example, of these examples of the P300, the evocated potential, the P300 evocated potential, and so on. Now, the advantage here is that you generate stimuli, which leads to a response by the system, by the user. In a typical example here is, for example, a matrix of 36 elements, for example, with numbers and names, letters and names, and you align them, align columns and rows. So what the user needs to do is concentrate in whatever letter they need to choose, or the number, and counting how many times that that element will blip, or either the row or the column to which it belongs, or the element itself. However, when it does, when it blips, when it illuminates, that leads to potential. 300 milliseconds later, and then when you analyze row and column, that you got a response in the encephalogram, you can detect the user's choice. So again, the choice here is that they don't need any training, but this kind of system are synchronous systems, unlike the previous ones where the user was conducting the position task. As for the objectives, is the development of an application that enables us to control devices to be able to conduct day-to-day affairs. People with severe disabilities. What we thought is, well, what BCI system do you use? Sensor motor ones or the potential 300? And we chose a P300 in the end because potential P300 because in a previous application that we tested with real users of a disability center in Lyon, we found that the user that managed to control the application the level of precision wasn't very good. Even some users didn't actually manage to control the application because in the training span, the weeks of training that we had, they didn't have the ability, they couldn't concentrate enough in these tasks. So the cognitive skills linked to the motor part of the brain affected their disability affected their ability to concentrate. So we chose a BCI based on P300, that is potential P300, because it didn't require so much training to see if it could work better. As for recording the G signal, we used a biomedical system with 16 channels. That's from an Austrian company, EITech. It's shown here in GTech rather, on screen. These are the electrodes we used, the gels, and the cap. We recorded 8 channels in the central, parietal, and occipital area of the cortex of the brain.